And then finally, there's a formula for the time dilation around a black hole. Okay, so understand that here's the singularity. Here is, of course, the event horizon, right? So this is our, imagine that that's a perfect circle, right? There's our Schwarzschild radius, right? And that we are like here. Okay, so we are some distance r from the center. Okay, r, of course, is bigger than rs, right? Okay. And don't be fooled, because sometimes in the questions I'll say, oh, you're this distance from the event horizon. That's not what you want. You want from where you are to the center. Right? So the distance that the clock is from the black hole, from the center of the black hole, right? From the singularity. Not how far you are outside the event horizon, right? But how far you are, right? And then that's the Schwarzschild radius of the black hole, is that one, right? And we know how to calculate that, so there it is, right? And then notice that this is set up, this is going to make this number bigger, right? And Stephen Hawking says this. I think we went to see him talk, and he said, well, okay, if you were to enter a black hole, or he says, as we say in the academic circles, if one were to throw a graduate student into a black hole, right, you would see them, and as they approach this event horizon, you can see what's going to happen here is that as your radius approaches the Schwarzschild radius, as it gets smaller and smaller, right, this thing approaches unity, and the time it takes for them to do anything approaches infinity, right? So imagine that the graduate student is waving to you as they fall toward their doom. Okay, as they approach the black hole, the event horizon, they're going to wave slower and slower until right at the end, right at the event horizon, their image will freeze, right? Because of course, this minus 1 minus 1 is 0. Anything divided by 0 is undefined. And as it approaches that, right, from the side, it approaches infinity, right? And so right at the event horizon, they will freeze, time will stop, and they will just sort of fade. They'll turn red and fade from view. So put this in there. Let's do this. And I'm trying to trick you in this thing, so we'll show you the trick. A graduate student is 5.5 kilometers beyond the event horizon of a black hole with a Schwarzschild radius of 9.5 kilometers. If they are waving in their frame of reference every 3.2 seconds, so that's going to be our proper time, right? How often do we see them waving if we are far away? So here's our, that's a pretty good circle. Here is our singularity. Here's our Schwarzschild radius, and we know that this is 9.5 kilometers, right? And then we know that we are 5.5 kilometers away. And we're sitting over here far enough away and big. Evidently, we're really big, right? Okay. And here's this poor graduate student, right? They're waving every 3.2 seconds, which is already pretty slow. Maybe they're not into it, right? Okay, we did ask them to sacrifice themselves, so there it is. So remember that we are going to go, that our time, right, is that proper time over the square root of 1 minus the Schwarzschild radius over the radius that we are at, the distance from there, right? Now, if you look at this, if you put the 5.5 as our radius and the 9.5, this becomes imaginary or something like that, which, there it is, right? But understand that the 5.5 is not our little r, okay? Little r is actually 9.5 plus 5.5. And I'm going to just go on a limb and say that that's 15 kilometers, okay? And then the Schwarzschild radius is, of course, 9.5. So we can now plug our numbers in here. So our time that we see them waving is the time that they are waving in their frame of reference, right? Over the square root of 1 minus 9.5 over 15. This is higher math. This requires the use of a calculator. Okay, so 3.2 divided by the square root, left parenthesis, 1 minus 9.5 divided by 15. I'm getting 5.2846 seconds between waves to that, which is about 5.3, right? Okay, so we see them waving slower and slower. And obviously, as r gets less and less, this becomes bigger and bigger. Eventually it approaches 1, and it takes an infinite time for them to wave.